Here we're taking a look at chapter 4. We're going to look at quadratic and higher order polynomial functions in this chapter. Specifically, in the first cluster, we're going to focus on those quadratic functions. We'll get to the higher order polynomials in cluster 2. So, in the first section, 4.1 here, we are going to look at some equations defining quadratic functions. We're going to talk about the form ax squared plus bx plus c of those quadratic functions. We're going to explore the role of each of those parameters a, b, and c. So the role of c, the role of a, and the role of b. Out of order, but we're going to look at each of those parameters and their role in terms of the equation. Cool. So let's get started. All right, so to begin, we're imagining that we're sitting on the roof of the Willis Tower in Chicago, and we're going to drop a baseball from the roof of the tower. And the height of the ball above the ground can be defined by this function, negative 16t squared plus 1450. Sketch a diagram, okay, illustrating the path of the baseball as it falls to the ground. All right, so first of all, we're on the top of this really tall building, and we're going to drop a baseball, and it's going to fall straight down. That's what's going to happen to the ball. So we just basically want to have a picture in our head about what happens when we drop a ball off the tower. It's going to fall straight down, and we're going to compare that to the image that we see later when we graph the function. So what happens is the h of t, the output, is the ball's height above the ground. So it's currently at a height of, we'll figure it out, 0. When you plug 0 into the function, you get 1450. It's currently at a height of 1450. Then after 1 second, what's its height? And after 2 seconds, what's its height? How far is it still off the ground? Okay, so we want to complete this table. So we're going to use decimals to get ourselves an autofill. Here we go. We better enter our function. H of t equals negative 16t squared plus 1450. And in our table, we want to plug in values up to 10 and have our function autofill those. Okay. So h of 0, like we said, was 1450. H of 1, 1434. 1386, and so on. And by the time we get down to the bottom of our table, our last value is negative 150. All right, so let's move over to our next page. How far does the baseball fall during the first second? Okay, so I moved my chart back over here so I can see. Let me focus real quick. So after 1 second, it has fallen down to 1434, but it was at a height of 1450. So we're basically trying to calculate the difference between those values, the change in height. I guess it was capital H in the previous page, the change in height. So the final height, which is 1434 for the first second minus the initial height, which was 1450, it's going to give us the change in height that we're looking for right here. So if we calculate that difference, 1434 minus 1450, it'll help us determine that we fell 16 feet. The negative signifies, of course, that it's a fall rather than a rise of 16 feet. So we fell 16 feet. Then it asks us how far it falls over the interval from 1 to 3 seconds. Okay, so at 1 second, my height was at 1434. At 3 seconds, my height was at 1306. So we're going to do 1306 minus 1434 and compute the difference here. And it fell a lot further. It fell 128 feet. Now, these aren't really comparable values because they're not over the same amount of time. This was over 1 second, and this was between 1 and 3 seconds. So it was a total of 2 seconds. So I might have expected this one to be twice as far, and I can see that that's not the case. But to get comparable values, what we really want to look at is instead of just the change in height, we want to look at the average rate of change, or the slope. So again, we've done slope plenty of times now in chapter 1, but we want to compute the slope um, over the first second and over the first and third seconds. So I'm going to move this out of the way. I don't need decimals for this part anymore. So the average rate of change or the slope over the first second, again, I can see the values up here. So after 1 second, my output was 1434 minus the initial output, which was 1450. But I'm going to divide it by the change in input. The final input was 1 minus the initial input was 0. So this gives us negative 16 divided by 1 equals negative 16. And the units on this would be, I forgot the units on input. Were they seconds? Yes. So this would be, I believe it was feet. Just want to make sure. Yes, feet per second. Okay, so again, now I can tell that it fell negative 16 feet per second in one singular second. So we're going to do the same computation over here for our slope over the between the first and third seconds. So again, I would have the 1306 minus the 1434, just change in outputs over change in inputs, 3 minus 1. So I have the negative 128 over 2, which will give me negative 64 feet per second. Now, these values are at least comparable in the fact that they're both slopes. They're both over a singular second. They're both per second. And so now I can say that, yeah, my rates of change are not the same. And so based on the results of part A and B right here, do we believe this defines a linear function? And we'll say no, because the rate of change is not constant. So the ball seems to be picking up speed, falling at an increasing speed the longer it drops. So the gravity is accelerating the fall speed of this object. So it's not falling at a constant speed. Okay, so what is the value of h when the ball strikes the ground? Use the table to estimate it. We're going to get a little bit better answer to that in a moment, but first we can just estimate it from the table. So from the table, we saw that our ball was at 154 feet above the ground after 9 seconds, and then it was down below the ground, which of course is model breakdown, by 150 feet after 10 seconds. So we can say that in between those two, it had to equal 0 somewhere in between those two. And they're about equal distance. I know there's that 4 distance between them. They're about equal distance though. So we can guess about 9.5 halfway between those two approximately is going to be where it hits 0. Rough estimate just from the table. We'll get the actual value later when we get to the graph. So we can approximate that after 9.5 seconds, the ball hits the ground. They weren't asking us here for the actual answer. They're asking us to use the table to estimate. And that can be done by the observation that the ground was about halfway between those two heights for the inputs of 9 and 10. Okay, what's the practical domain? All right, so the practical domain is the inputs that are going to make sense. And again, looking at my inputs, 0 is when I first dropped it, so I can't go below 0. And by 10, I've already broken down because I'm underneath the ground. So that 9.5 is going to be our estimate for the upper limit again of when the ball is going to stop falling. It's going to stop falling when it hits the ground. So we'll estimate our practical domain as the values between 0 and 9.5. Practical range. Okay, so the range is the height, the output. And I know that the ball started at a height of 1450 and it's going to fall until it hits the ground. It's not going to go underneath the ground. It's not going to burrow through the earth. It's going to hit the ground at 0. It's going to stop. Intervals have to be in order. So the 0 output value has to go first and the 1450, the larger output value, has to go second. So my range, I'm going to say it's going to be 0, lowest, up to 1450 as the highest height that this ball achieves. It starts there, but then it falls down to 0, and these have to be in order of lowest value to smallest value for an interval. Okay, then we get to sketch the function on the practical domain. So I am going to rescale my graph based on what I have said for my practical domain. We've said that the practical domain was going to be from 0 to 9.5 and from 0 to 1450. So let me turn off the graph settings, zoom out just a teeny tiny bit so I can see where the axes are. We're starting up here and we're coming way down here to that 9.5. So the graph is going to look something like that, okay? Roughly like this. And this height up here is our 1450. This height right here is 0. This input right here is 0. And this input right over here would be 9.5. Again, rough scale representing the path of this ball. So is the graph of the height function the actual path of the object? That's where we compare to the graph that we drew over here. This ball falls straight down. So this is not the actual path of the object. This is a spread apart graph where we are examining time as a horizontal. It's not a horizontal distance. The ball is not arcing away from the building as it falls. It's falling straight down. So this is not the actual path. Okay, so this just has time as one of its variables. The ball fell straight down. This is not the actual path. And the reason it's not the actual path is because, let me move my book here. This distance over here, this is not a distance, I should say. This axis over here is time. It's not horizontal distance. So the x-axis is time, not left, right, not horizontal distance. Okay, on to our next page. Okay, now we're going to look at this same function, but we're going to look at it out of the practical context. And so we're going to just generalize it. Let me pull it back over here, get rid of some of the computations I did. I'm going to get rid of the table as well. And they said, just call it y and such and call it x. I'm just generalizing it. So we're not in context anymore. And then they would like us to rescale. So they want us to rescale so I can see some more values. They've got a negative 10 and a 10 on the x-axis. And a negative 50 and a 1500 on the y-axis. So I can see the full graph right here, and I can see both sides of it. Both sides of it did not make sense in terms of the practical case because all of these points over on this side that had negative times just didn't make sense in the context of dropping the ball as the ball had not yet been dropped. So I didn't graph this side prior, but now I can see both sides of this graph. And I can see that the topmost point of this particular graph is at that 1450, that height where this ball was dropped. And we had previously graphed just this side of it. Now I can see both sides. I could even zoom out a little more. Of course, it does go down below the x-axis. Again, for practical, we stopped at the x-axis because it represented ground level, but the full graph of the function does go beyond in both directions. All right, so describe the important features of this graph, discuss the shape, the symmetry, and the intercepts. Okay, so it has a upside down U shape, or the name of the shape is the parabola. The parabola can either be a U that faces up or a U that faces down. So the shape is a parabola. Okay. It is symmetric around the y-axis. If you spin around the y-axis, you see the same thing happening on the left side and the right side. So there is some symmetry there. It has a y-intercept of 0, 1450. And it has two x-intercepts. And I don't know what they are yet, so let's find out. Negative 9.52, 0 and 9.52, 0. negative 9.52, and 9.52 comma 0. So we had guessed earlier that the x-intercept on this side was going to be 9.5. So we weren't too far off with 9.52 from our guess based on the table. Obviously, the graph gives us a little bit more precision than the table. And if we were able to solve this algebraically, we'd get even more precision again. So one of the things that is nice to note about this one is that there are two x-intercepts. And this is something special to the quadratic functions as compared to the other types of functions that we talked about before. When we talked about exponential functions, linear functions, logarithmic functions, they had one or none. None of them had two x-intercepts. And our quadratic function does here have two. So just a distinct point to note about quadratics as a new class of functions that we're studying. Okay, so now we are looking at our equation. Anything that is written of the form y equals ax squared plus bx plus c, or as a function, f of x equals ax squared plus bx plus c, where a, b, and c are real numbers and a is not 0, because if a was 0, it'd be linear, right? Bx plus c would be linear. Ax squared plus bx plus c is a quadratic function. And the quadratic term is the ax squared term, the linear term is the bx term, and the constant term is the c term. So we have three different terms of different degrees. The squared term is called the quadratic term, the linear term has degree 1, and the constant term has degree 0. And we use the word coefficients to talk about the coefficients a, b, and c. Well, technically a and b, because coefficients should have a variable. We kind of call c a coefficient sometimes, but other times we call it a constant. All right. So let's look at these four quadratic functions. We just want to identify what their a, b, and c values are. So for the first function, the a value is 3, because I have 3x squared, the a value is going to be 3. I don't have any x's, I don't have any constants, so that means that b and c are both 0. There are always terms for b and c, even if they're not listed. So if they are not listed, they must be, because there's 0x here and 0 as a constant. All right, in the next one, negative 2 is going to be the a value. There's no x's, so you're going to have 0 for the b value, and the c value is going to be 3. In the next one, the x squared term there's one x squared there, so we've got the invisible coefficient of 1 x squared, so 1 is our a value, 2 is the b value, and negative 1 is the c value from the constant. And in the last one, negative x squared means that negative 1 is the a value, 4x, 4 is the b value, and I don't have a constant number, so my c value is 0. So just a little bit of variety here to see what different quadratic functions can look like depending on what their values for a, b, and c are. Note that the a value cannot be 0. It's not 0 in any of these. A cannot be 0, because if a was 0, there wouldn't be a quadratic term, and then this would not be quadratic. It would be linear instead. So b's and c's can be 0, but a is not allowed to be. Okay, the constant term c, a closer look. Okay, so back to our graph of the baseball dropping. What's the vertical intercept of the graph? We had already identified that as 0, 1450. Explain how we obtained the results. We clicked on it. That would have been one of the ways that we found it. But we also could have found it by plugging 0 into the function. So h of 0 is negative 16 times 0 squared plus 1450, which is 1450. When you plug 0 into the function, any place that has a variable is going to become 0, and there'll never be a 0 on the c value, so the c value is going to correspond with the vertical intercept. So just a note down here, the constant term c always indicates the vertical intercept of the parabola. So the vertical intercept is that ordered pair 0, c. Yeah, because when you plug in 0, a times 0 plus b times 0 plus c is going to equal c. Okay, what's the practical meaning of the vertical intercept? So initially, the ball is dropped from a height of 1,450 feet. After 0 seconds, right? That's just where it's dropped from. predict what the graph would look like if the constant term were changed to 800. So if my function were instead negative 16 t squared plus 800. Okay, so instead of the function being up here at 1450, I would predict that it would be down here at 800. That's my prediction. So my prediction is that it would have 0, 800 as its vertical intercept. All right. And you can graph it if you'd like to confirm that. All right, so number 8, graphing parabolas defined. Graph the parabolas defined by the following. Note the similarities and differences among the graph, especially the vertical intercepts. Be careful in your choice of window. So it wants us to graph each of these. Okay, so they are very similar functions. So I'm going to pull the book down a little bit and just graph them all. So I've got f of x equals 1.5x squared. I'm going to resize my window here. It does say be careful of your choice of a window. I resized my window away from the one that had the huge y-intercept of 1450 because I didn't need to be that high anymore. So I jumped back to a standard window and then zoomed out a little bit. And that seems to be sufficient for this graph. So now I want 1.5x squared plus 7. Oops, I hit the wrong key there. I didn't hit plus. There we go. Okay. And then I want q of x equals 1.5x squared plus 4. Okay. And I want s of x equals 1.5x squared minus 4. Okay. So all of these graphs should have the same shape and size, but if you imagine picking one of them up and moving it up, you'll be able to get to the others, or down, vice versa, to get to the others. So the original, I would say, this first one, this green one, the one right here, was from f of x. And then the other graphs were either this same graph pushed up by 4 or by 7 or pushed down by 4. Okay, so I'm going to make notes here. Let me pull the decimals part up and say that all graphs have the same shape as f of x equals 1.5x squared. And then part B and C, b of x and q of x are moved up by 7 and 4 respectively. And s of x is shifted down by 4. All of the same shape. They've just been shoved up, shoved down based on their C value, because their C value is just changing the y-intercept. The y-intercept of the first graph was 0, 0. Then we have 0, 7 as the y-intercept, then 0, 4, then 0, negative 4. All right. That talks about C, the effective C. Now, each of these was a C value, right? They had the same A, they had the same B. The only thing that changed between these four functions was C. So we're examining what C looks like, how it changes the vertical intercept and pushes the graph up or down. All right. In the next part, we're going to look at the coefficient A and discuss how the coefficient A seems to affect the graph. Okay, so we want to go back to these two functions. Okay. Let me hit undo a couple times and see if I can get that function and its window back up. Come on. It's a lot of typing to undo. All right, there we go. So I got one of the functions, and the other one I want to be the same thing, except without the negative. Ooh, there it is. Okay. Okay. So what effect does the sign, positive or negative, of the coefficient of x squared appear to have in the graph of the parabola? The shapes are the same, but they are reflections of each other. One faces up, one faces down, so it controls the direction. So if it was a negative sign, then your parabola faced down. Like the original shape, right? And if it was a positive sign, your parabola faced up, like the new graph. That seems to be the effect of the sign, because nothing else changed, just 16 and negative 16 was the coefficients, that was the change. So it appears to control the direction that the parabola faces. Okay, so some more modifications to our graphs. We want these, let's take away the bottom one. Okay, and I want, let's see, negative 16 t squared plus, oh, we're changing it to just 100, so I better shrink my scale down here. I don't need to be all the way up to 2000 anymore. Okay, good enough. Okay, so I want one of them to have a negative 16, one of them to have a negative 6, and the third one to have a negative 40. Okay. All right. So I'm going to make the original one dashed just to make it easier to see which one it is. So the original one with a negative 16 is dashed. What effect does the magnitude or size, the 16, so ignoring the sign, ignoring the negative, the 16, the 6, the 40, those are the magnitudes. The magnitude just is the absolute value of the size, not the sign, appear to have in the graph. So if the magnitude got smaller from 16 to 6, it got wider. And if the magnitude got larger from 16 to 40, it got narrower. Interesting. Okay, so the smaller implies that the graph gets wider, and then larger implies that the graph gets narrower. That's what I observe. Okay, so they're going to summarize this for me in a box here. So there are two things that A does. Okay, the coefficient A can do two things. C just did one thing. C controlled the vertical intercept. A can control two things. If A is greater than 0, so if A is positive, that means that your parabola opens upward. So our parabola opens upward if A is positive. And if A is less than 0, if A is negative, then the parabola opens downward, as we observed on the previous page. So the sign, positive or negative, will help us determine if the parabola is going to open upward or downward. Then the magnitude of A affects the width. So the larger the absolute value of A, the narrower the parabola. And conversely, the opposite is also true. We might as well write it in. So, and the smaller the absolute value of A, the wider. They must have thought they didn't need to say both things, because if it gets large, it gets narrow. So the opposite, of course, is that if it gets small, it gets wider, but it doesn't hurt to state both things out. The larger, the wider, I'm sorry, I can't talk. The larger, the narrower, the smaller, the wider. That is what I meant to say. That is what we have observed up here to be true as well. All right. So, is the graph of 0.3x squared wider or narrower than the graph of x squared? Well, its coefficient, 0.3, is smaller than the coefficient of 1. This one has a coefficient of 1 right here, right? And since it is a smaller coefficient, it's going to be wider. Because 0.3 is smaller than 1. How do the output values of h and the output values of f, these two functions, compare for the same input value? Well, the output values of h should be smaller, lower, than the output values of f. Smaller or lower, if you want to look at it that way. Now, I'm doing all this right now based off of the information I know about A, but let's go ahead and look at them graphically to help us confirm this. I'm going to go to the home window and we're going to do our two functions. We've got our h of x, which is, I forgot the 0.3, 0.3 x squared, and we've got our f of x, which we want to just be regular, x squared. Okay, so I'm going to make, I like to make the standard one, the dotted one, just f of x, because the one that we're emphasizing right here, h of x, it is wider and it is lower or smaller, the outputs. So that means if you're looking at any specific input, like x equals 2, like one specific input, the outputs of h are lower, smaller, or lower than the outputs of f. For the input 2, the output of f is 4, and the output of h is 1.2. So again, it's a smaller or lower output value for our h of x function. That's what we are saying up here, and that's what we're also observing in the graph. All right, so let's do the same thing with the next one. Is the graph of 3x squared wider or narrower than the graph of x squared? Well, 3 compared to 1, this is going to be a larger value, so this one is going to be narrower. Because 3 is larger than 1. How do the outputs of G and F compare for the same input value? So the outputs of G are larger or higher than the outputs of F. And again, we can look at this one graphically. If I just take away the 0 point, we're going to have the comparison with 3, and you'll see that, again, the h of x function is narrower than the f of x function. And if you look at a singular input, the output is going to be larger or higher for the h of x function than it is for the f of x function. For the input of 2, 12 is a larger, higher value than 4. Okay? So once again, you can see that you're narrow when you have a larger coefficient. Describe the effect of the magnitude of the coefficient A on the width of the parabola. Okay. Can we just draw an arrow and say that this is the effect? The larger the absolute value of A, the larger the magnitude, the narrower the parabola, the smaller the magnitude, the wider the parabola. Okay, so larger makes them narrower, and smaller makes them wider. Okay. All right, and describe the effect of the magnitude of the coefficient A on the output value. Okay, so instead of phrasing this in terms of narrower or wider, we can phrase this in terms of larger and smaller. So the larger the magnitude, the larger the output, and the smaller the magnitude, the smaller the output. Okay, so that talks about A. And last, we're going to talk about B. So we want to talk about the effects of the coefficient B on the turning point. All right. So we are going to start with graphing these two new functions. I'm going to compare with my directions. We're going to be on the next page. So let me move decimals back over here. I'm just going to start a new one instead of undoing and all that. Okay, so I'm going to do the first function, h sub d, I guess. I don't know. I'm going to be allowed to call it h sub d. Maybe not. And we want negative 16 t squared minus, looks like I'm allowed to use this name, good, 40t, and then plus the 1450. So I had to rescale this real quick so that I can see where 1450 is. I'll just pop up to 1500. Oops, 19,000. And I don't need all those negatives. Okay. All right, so that's our, okay, that's our function. And the other one, hu of t, is going to be the same thing. Oops, I don't want to copy the function name. But with a positive 40 instead. Okay. So in the first case, we are not just releasing, we are throwing the ball downward. So we're not just going to drop it, open our hand and drop it. We're going to chuck the ball downward. And then in the last case, the bottom case, we're actually going to throw it upward instead. All right. Now I want to compare these functions with, I want to predict actually before I compare. So I want to predict what features the graphs of h down and the graph of h up have in common with this one. Okay, so I'm going to predict, was I not supposed to graph them because I did already? Whatever, maybe I wasn't supposed to graph them yet, but I'm going to predict that they have the same shape. Okay, and I might predict, because I know I'm throwing down versus throwing up, that I might move faster downward and I might move slower downward if I'm throwing up or throwing down. Okay, so the same shape, and I would predict that h down hits the ground first, and h up hits last. I'm going to throw it up. It's going to take it longer to the ground. That's my prediction. Okay, now graph all three. So I need to graph my h of x function, my regular h of x, or h of t function as well. Okay, I'm going to dash this one just to make them easier to distinguish. What is the effect of the negative 40 and the positive 40 term seem to have upon the turning point of the graphs? The turning point is the point at the top of each of the graphs. It appears to shift it to the left and shift it to the right. That would be my prediction. So the turning point shifts to the left and shifts to the right. Okay, and so our conclusion about B here is that if b is equal to 0, like it is in the original function, then the turning point is on the vertical axis. So if I turn off the other two for a moment, the turning point of this one's right on the vertical axis. But if the b value is not 0, you're going to get a turning point that is not on the vertical axis. So it just got shifted left or right. So if b is not equal to 0, the turning point is not on the vertical axis. That's one of the things that b tells us. It tells us something about the location of the turning point. Okay. Now, we could go a teeny bit better than that and say that the negative 40 shifted the turning point, moved it to the left, and the positive one moved it to the right, although it's not because the 40 is a negative, it's actually because these have the same sign. So it gets a little more complicated. It's not the same sign or different sign from the original about whether we're moving left or right. So we'll just leave it right here. That's a conversation for Math 139 where they talk about horizontal translations. But right now, we're just going to note that it does shift it left or right, and we can graph it to verify which of the two it is. Okay, so for each of the following quadratic functions, identify the value of b, and without graphing, determine whether the turning point is on the y-axis or not. Okay, I can do that. So in this one, our b value is 0, so that means that the turning point is on the y-axis. Here, the b value is negative 4, so the turning point is not on the y-axis. Here, the b value is 0, so the turning point is on the y-axis. Here, the b value is, the coefficient of x is 1, so the turning point is not on the y-axis. And here, the b value is 0, so the turning point is on the y-axis. Okay, so you want me to graph them? Verify? Yep. Easy enough. So we will make a new graph real quick. I don't need these functions anymore. And graph each of these. So y equals x squared. Turning point right there on the y-axis. Let me pull this to the top. Next one, x squared minus 4x. Turning point, not on the y-axis. It's over here, not on the y-axis. Okay, x squared plus 4. Turning point right there in the y-axis because b is 0. X squared plus x. Turning point, not on the y-axis. It's somewhere else. And x squared minus 3. Turning point right there on the y-axis. So verified. Okay, and then number 15, match each function with its corresponding graph below, then use your calculator to verify. Okay, so I'm going to use what I know about these functions. Okay, first things first, in this first function, there's a positive a value, so I know that this thing faces upward, so it's not that one. I also know that the turning point is not on the y-axis because of the 4. So I also know that it is got a vertical intercept of 0, 4. So I can look at A, B, and C and get information from all of them. So this is the vertical intercept, 0, 4 from the C value. So it is this one, right? So the A, f of x is going to be this I. A, f of x, it's going to be this graph right here. Okay, now I look at the next one. Faces up. It's a little bit on the wide side because of the 0.2 and the turning point from the b value. So the b equals 0, and so that means that the turning point is on the y-axis, And then wait a second. I messed up. I'm sorry. Um, I said in the first one that the turning point is not on the y-axis. Then I went and picked one that was. This turning point is on the y-axis. So that's not going to work for this one. The turning point needs to not be on the y-axis. So it had to be this one whose turning point is not on the y-axis. So this is my f of x. I apologize. I stated the correct information up here, then I ignored it for, I don't know why. I got distracted with my picture. Okay. Now, this one we said, facing up, the turning point is on the y-axis. Is on the y-axis. We also said, because of this 0.02, that it was going to be wide. And so this one's going to be g of x. And then the last one, what we know about that one is that it's got a negative coefficient, so it's going to face downward. And then its turning point is not on the y-axis. So not on the y-axis, this one could be h of x. Okay. And it would like us to graph them to confirm. So I start with the x squared plus 4x plus 4 matches graph number 2. Looks good. Graph double I number 2. Then I have 0.2 x squared plus 4 matches graph number 1. Good. And then I have negative x squared plus 3x matches graph number 3.